Okay, so I guess before the break we saw this list entries, saw how to make it efficient. I guess I'm just gonna write it again in the simpler format here where while they exist. C with C count 1. Some value sum output. Some value sum. And then this original paper by Goodrich and Itznaga, they want to analyze what is the probability that this succeeds in outputting all the key value pairs when we're below the threshold in the number of key value pairs. And let me just say briefly how they do it, and we're going to do it differently. Also because there's a bug in the proof in their paper, the conclusion is correct. There's a mistake. What they do is they say, okay, they actually present it slightly differently than what I did here. I had this K by 2G table. They instead look at one table whose length is something like some constant, depending on K, K times T. So it's basically the same, but just collapse it into one long list instead. And then they have one hash function that gives not one hash position, but gives K positions. And then they analyze it as if this hash function gives a uniform random set of K distinct positions. And then you add it to those. So it's a slightly different way. It's a little bit harder to implement such a hash function in practice, I would say, like how do you implement something that gives K distinct positions. The reason why they do it like this is because then it allows them to reuse I guess some results that people have looked at before to bound this probability. Now I'm just going to give you their analogy and how it works in their analysis, and then we're going to give an action analysis with this one with all the details. So what they observe is they say, okay, they want to understand what is the chance that this so-called is called a peeling process, where you kind of, whenever there's something with the count of 1, extract it. So they relate it to something that's been studied in, I guess, combinatorics relating to hypergraphs, random hypergraphs. So what is a hypergraph? I guess a hypergraph is like you're used to. It's a graph. So you have nodes. So in this graph you have nodes like you have in normal graphs. Then you have so-called hyper edges. So what's a hyper edge? And hyper edge is just, well, you can think of a normal edge as a set of 2 nodes. Hyper edge is just a set of 4 nodes. Okay, so you can say here, I guess you can have a hyper edge here that consists of 3 nodes. Maybe another one here that consists of 3 nodes. And generally, you say that if I have a hypergraph where all the edges consist of K nodes, then it's called a K regular hypergraph. So now they observe, okay, when I have my keys x1 to xn, and they're distinct keys, then I could say, okay, for each of them, I can think of it as there is an edge on those K nodes that I hash to. Right? So I think of it as there's a node for every cell in my table. Oh, here's just an array. So we have a node for each cell. And then for each of my keys, I have a hyper edge. Okay, so this is so basically this corresponds to hash of x1, and maybe this corresponds to hash of x2 in their setup, where a hash function maps to 3 positions in this case. So then you get a 3 regular hypergraph if you have hash to 3 positions, and in general you get a K regular hypergraph. Does it make sense? This is what they look at this graph, and then they observe if my hash function h is truly random, then this hypergraph I get is what's called I guess it's called a random K regular hypergraph. So just every edge is a random set of K distinct nodes. Okay, so it's a random irregular hypergraph. And then they observe again that this peeling process here, so we keep deleting stuff with a count of 1. That corresponds to a well-studied kind of process also in random hypergraph theory. So what they look at is something called the 2-core of a hypergraph. So what is the 2-core of a hypergraph? It's basically what I get if I repeatedly look at, is there a node, so a node here, one of the nodes here, of degree less than 2. This one has degree 1 because it's only part of one hyper edge. If I repeatedly find nodes with degree of less than 2 and delete its incident edge, then when this process terminates, I have the 2-core. Yes. The 2-core is really, I guess, the remaining graph once I keep deleting all the edges with a degree. Whenever there's a node of the degree of 1, I delete the incident edge. Then I'm left with the 2-core. That's just terminology now. So basically, this process terminates with everything being output and extracted whenever the 2-core is empty. Like the same thing, right? When the 2-core is empty, this is the same place as the ListEntries terminates and has output everything. And then the reason why they draw this analogy is because this is a well-studied thing. So you can just look up in some papers on combinatorics, what is the probability the 2-core is empty? When I have, I guess I have here, I have, let's call it M equal to CK, KT nodes, and N edges. This is the setup of parameter. Because we get one edge for each of the keys that's stored. We get one node for each memory cell in the data structure, and then you can get an expression for this. And one thing that what you get is basically with this setup of some constant CK, you get order, and let's see here, T to the minus K. This is what you can then look this up in some math journal paper and find a bound like this. So let's have a look at it a little bit. So if you remember the get operation we looked at before, right? That one's failure probability was 2 to the minus K. Here it's basically T to the minus K. T is at least N, right? This is like N to the minus K versus 2 to the minus K. So it's a much better failure probability. It goes down much faster, which is pretty interesting that you actually, this peeling really helps you get even better than the get operation by doing this peeling. Of course, I think that maybe, I think they were also, that paper was written more to practitioners, so I guess it makes sense to just invoke some theorem that has already been proved. They also include a separate proof that does not give us type constants and so on as a proof you can look up here. But it's in that proof that there's a mistake. Okay, but it is some simple mistakes on some binomial coefficients. So what we're going to do is we're just going to prove it from scratch for our formulation of it and see how it goes. Right? So we're going to prove this bound here. And we're not going to worry more about hypergraphs or anything. We're just going to look at it directly. But it's the same proof as they sketch in their paper, just done without any mistakes. Okay. Now let's see. I'll have to delete this to fuses. Okay. And this is probably going to be the biggest union bound we're going to see in this. So it's quite large. So let's start by defining this event that we fail. Let's call this peeling. Maybe let's just say ListEntries fails. I did like this. Let's say we have keys x1 to xn. These have been inserted and n is less. And I think for this analysis, just to make the constants a little bit prettier, I'm going to change the size of the table a little bit so that it's still k on one side, and here it's going to be e squared t. So just the natural number squared instead of 2. It's just to make the numbers pretty. So we'll see that this is a little bit more convenient. So let's say e squared t. Okay. So we want to upper bound the probability of f. So what do? We do like we tried several times, of course, we try to split it up into simpler events that we can then kind of union bound over. So this is what we want to try and do. So let me write it here. So let's define another event. Fj is list entry fails. With j pairs left, the key value pairs left. Let's write it like this. Makes sense. So the end to begin with, I start the peeling, and eventually it stops, and I haven't peeled everything. So let's just say Fj is the case where it fails, and that j pairs left that have not been peeled. Because then we can say, okay, well, whenever we fail, we fail if and only if at least 2 t's left. Right? Makes sense? If there's only one, then the peeling will not fail. Actually, one place. We can do like this, and then we can use the union bound, of course. So this is, now we have split it into a sum. N of FPA. Now we'll say, okay, let's try to split it into even smaller events. Now we're going to define an event for every set S. S here is a subset of x1 to xn. The size of S is equal to j. So we're going to define f js. List entry fails with S, the remaining keys. Make sense? Just saying peeling, the peeling process fails, and S is the set of keys that are left. So then we can say, okay, can work with this probability of Fj, of this event Fj. We can also say, well, Fj is also the union over all S. Let's write it like this in n choose j. This is all the subsets of size j out of our n elements. This is just abuse notation a little bit. So all the subsets of size j of f j s. Make sense? And this is actually with an equality. I guess. So I guess here we can use the union bound again, right? And this time, if you actually get this inequality because they're disjoint events, but I guess you could also, an upper bound is fine. We just do this sum, and then I guess we're going to sum over all S. What I'm saying is this is an equality, because if I say that there's exactly S elements left, only one of these events can happen at the same time, right? Only one particular set of j keys can be left. But anyways, you can just put a less than equal to it, and the union bound gives. Okay. So basically, we're just splitting into which are the keys that are left when I'm done peeling, the ones that I couldn't peel. And now here comes the last kind of interesting thing, and then I don't know. This I guess is the trickiest part of it. Where do I want to put it? Maybe there's a little space down here. Okay, so let me put it in the bottom. So now I'm going to say, okay, so now I'm going to define a whole lot of events. I'm going to define case sets, and they are all subsets of is E squared T, the number of columns, and they have size J half. Okay, and then I'm going to define an event F, J, S, T1 to TK. And this event is going to say all, say, X, I, and S for all H equals 1 to K. H, no, not, it's called A. HA of XI is contained in TA. Okay, so let's try to see if we can figure out what this means. So what am I saying here? So I'm saying, look at this table here. Look at the table. Now the sets T1 to TK, they are going to pick out J half entries in each row, right? So T1 picks out J half entries in the first row. T2 picks out J half entries in the second row. T3 J half entries in this row. And then I'm saying that for all the keys that I couldn't peel, for all the rows, it holds that my hash value is contained in this set of indices that I picked. And now my claim is, and this requires a little bit of argument, is that this event here is contained in the union over all these events here. So the claim is that the event if JS is contained in the union over T1 to TK if JS T1 TK. Let's try and stare at this a little while. So we're saying, my claim is, if the peeling fails and S here is the set of keys that are left, S is the remaining keys. When that happens, it must be the case that there is at least one set of sets, T1 to TK, where my hash values end up in these sets. And these sets have size J half. This is a little bit of a tricky statement, so let's try and look at it. So let's do that. So why would this be the case? So I have my table here. I have a set S of some keys that are left, and I cannot peel anymore. Each of these keys, they end up in one position in every row. What can I say about the counts in the cells of these rows? Like, what are the possible values of the counts when this peeling process stops? You cannot keep going. What are the possible values of the counts? Yeah. 0. Yes. All the counts are either 0 or at least 2. Make sense? Otherwise, I could, if there was a count of 1, I could keep peeling. So if I look at these keys here, there are J of them, and they hit these keys, they hit the cells, and there's always at least 2. Like, this in every one of them. Something like this, right? So I know that there's, so okay, so now my question is, how many non-zeros could there be in any row? How many cells with a non-zero count? What is the maximum number of cells with a non-zero count in any given row? Yeah.
J over 2.
J over 2, right? Because every non-zero has to have a count of at least 2. We know in every row the sum is exactly J, but the J things left. So the number of non-zero counts, let's make it to J half. Okay, And I guess in this case, j is 6, right? This example here. So my claim now is that, well, there has to be a collection of j-half-sized subsets where all my hash values lie in these j-half. In particular, like j-half here is 3. And let me draw. Okay, so I can pick these two, and then I can pick an arbitrary one, like this one. Like here, I have to pick those. Here, I can also pick an arbitrary set. Right? So whenever peeling fails, it is possible to choose j-half entries in every row so that all my hash values end up in these entries. This time, no, there can actually be multiple choices. Right? I could also choose this one here. So I'm really just, so that's what this claim is saying. I'm containing this union. This might not be a disjoint union. Or what can I say? Like my set could actually, multiple of these events could happen at the same time. Like, so that's not a given, but this is still fine, right? My event is still contained in the union of these sets. So that is the kind of key insight that, and actually this j half turns out to be crucial for the computation. That it's j half instead of j. Otherwise, things will not work. We're really using that you have to have two that hit every non-zero is at least two. Kind of the key observation. So now we can continue here and say this is less than or equal to sum to n sum over s and choose j sum over t1 to tk in e squared t choose j half. And then let me just use the union bound. I guess I already used to put it into a sum instead of just the union here. So then it's f j s t1. And now we have something that is kind of simple. This event here we can actually analyze. So let's have a look at this one. So what is the probability? And here we're actually, universal is not enough. Here, let's say we have a truly random hash function. Right? Our hash function is truly random, meaning that all the hash values are independent. Let's say truly random. What can we say about this probability? All right, so basically think of it, I already fixed the sets T1 to Tk, they're fixed, they're not random. I fixed my set S. I know the size of S is J. What is the probability that for all the keys, for all the rows, my hash value lies inside this set? What can I say about this probability? Yeah.
Also, the inner fall is like dependent.
Yep.
You can post by those. Then.
Yeah, we have a truly random hash function. So for different keys, everything is independent. Yes. So we have a product over all of those. Yeah. We guess we have the product over x sine s, product over a equals 1 to k. Yes. And what about this inner probability? What can we say about this? What is the probability that my hash value lies in a particular set? It's a truly random hash function. Yeah.
The size of the set divided by the size of the universe. So j half divided by square.
Yes, exactly. Just the size of the set divided by the size of the universe. So this gives us, so the size of the set is j half divided by the e squared t. And then I guess raised to the kth power raised to the j. So this is the probability, and now we can insert it into our giant union bound. Getting messy here. We just move down a little bit. So, okay, so it's the same for all of them. So now let me just turn it into so there's a sum again from j equals 2 to n. The number of choices for s is n choose j. The number of choices for t1 to tk, well, for one of them, this is e squared t choose j half, and we have to choose k of them, and then we have to choose and then we have this probability in here, k over 2 e squared t k. This is our final expression here. Okay. And now the rest is just arithmetic. So here we're going to use as a standard upper bound on the binomial coefficient that we're going to use, and it's just saying that n choose k for all n and k is less than e n k. This is standard inequality for the binomial coefficient, and we're going to use it on this one and that. I think the black is starting confusing for the eyes, so let's just turn in blue here. N E N K J squared times T over J. Let's move the 2 up. J half times the K, and then the other one here, J 2 squared T. And now I think we can start bringing together some terms. Let's still keep the outer one. Let's keep the first one for now. Now let's make the exponent kj half. Let's have a look at what are the terms that we have. So, like you can see here, there's a j to the kj divided by a j to the kj half. If we bring those together, I guess we just have a j to the jk half. Let's put that on top. Right. That's those two. Here we have a divided by t to the kj multiplied with the t to the kj half. So that's just divided by t to the kj half. Okay. We have, let's see, we have a divided by 2 to the kj multiplied with the 2 to the kj half. That's again a divided by 2. Then we have all these e's. So I guess we have a e squared to the kj half divided by an e squared to the kj. So that's divided by an e squared. Those two. So that's divided by an e squared to the kj half. And then we have another e to the jk half. I guess that's just divided by an e to the jk half. So it's simplified quite a lot if you just brought together these two terms. Okay. And maybe let me just point out again here that it's really crucial. Maybe it's hard to see where the magic is happening. The really crucial point is that this exponent is kj half. That comes from these sets being j half in size. This is really where we're gaining something, because if we allow these sets up here to have size j instead of j half, and this wouldn't cancel out as nicely. It also makes sense that if I'm saying I have j keys and I have sets of size j, what's the probability that my hash values lies in the set? There will always be a set of size j where my hash values lies inside. Right, so it's really crucial here. This half size, that's what makes it all work. So now we have this expression here, and then you can stare at it a little bit and try to figure out what's happening here. This is kind of growing in j, yeah. This is maybe decreasing up to some point. So let me just show you what is the right way to bound it. the right way to bound is to pull one of these terms out. So then I have 2n n over j to j. Now I want to pull one term out that is this other one here that's also raised to the j. If I do that, then the remaining term here is now should be raised to the k half minus 1 here. Makes sense? So I just pulled out one of the powers where I raised it to the j. Because now these two kind of work nicely together. This one cancels that one. This one cancels that one. And then we get, this is another reason why the e squared was a nice choice. So then we get n over 2t j. And then we have this other term j over t is at least n, right? T is at least n. So this is at most a half, meaning when I raise it to a higher power, it becomes even smaller. Right? This is something that's at most 1/2. It's actually at most a quarter. So we can also just say, let's just upper bound it and get rid of the first term. And then we have the second term here. What do we see here? We also see, if we stare at it, that j is always at most n. So this is always something that is, I guess, like this is less than some 1 over a big constant. Becomes even smaller as I increase j. So this is probably see it write this as a geometric sum that goes down, and it's basically the first term is the one that matters. Makes sense? Whenever I increase j, this goes down by at least some constant factor. Is that obvious enough to everyone? This is always something that is significantly less than 1, a big constant less than 1, and whenever I increase j, I increase the exponent, it becomes even smaller. So let's just say this is order the first term where j is 2. So if I insert j is 2, I get 1 over 2e, but let's just say 1 of that et, so let's just say 1 of t. And then this is raised to the, insert the first j was 2, then I get k minus 2. And this is the one we claimed to begin with. I think maybe it's been erased. Right, so it goes down as t to the minus k plus 2. It's the chance that this works. So yeah, so this is the, I guess, the giant union bound where we just can say, okay, what, we just zoom in on what can go wrong, simplify it in until you're left with just this particular set of j keys, a particular set of j half entries in every row that they must hash to, bound that probability, and then you just work out all the sums. A little tedious, but there's nothing more to it than just working with these binomial coefficients. Nothing magic happening. And then you get this very nice bound of t to the minus k plus 2. Let's see how we're doing on time. I think maybe there's like 15 minutes left. Let's just continue now and finish early instead of having a break and having 5-10 minutes after the break. Okay. So that takes care of this list entries operation that we also talked about. Now we've seen all the operations. And I guess this one had this failure probability of t to the minus k, and this one had this failure probability of t to the minus k plus 2. That makes sense to have k at least 3, right, in this analysis for this to go through. And there was one thing that we skipped here. We assumed that you did not have these false deletions. Right? Like, so we only deleted things that had actually been inserted. And all the analysis was done under that assumption. So I think what I'll spend the last little bit of time on is just saying, how can we handle it if there's also false deletions? Too many. So you can also delete something that was not there. The requirement for it to work is that the number of actual pairs plus the number of falsely deleted pairs is at most t. So then that's the requirement for it to work. So number of actual pairs, well, then pairs dot plus false deletions. If this is at most the threshold, then it will work. And if you remember this application with the two servers, like one of them inserts all the keys in one database, sends them to the other server that deletes all the keys in that database, the number of false deletions is the size of the second set minus the size of the first set. The number of false insertions are the elements that are left is the size of the first set minus the size of the second set. So this n is this symmetric difference. That's a small difference. They're almost the same set. And so the two sets, right, we have SA minus SB. This is the pairs that are left after the deletions done by B. And then we have SB minus SA are the falsely deleted. As long as this sum is at most threshold, then our modification we see will still work. So let's have a look at how could we modify these operations. We're going to do the same in the insertion deletions. We're just going to insert them, and except for one thing. So we're going to add something to the data structure. Let's say here. So we had it up here. So here the thing we're going to add one more thing to each cell, and that is what we call a hash sum. This, and then we're gonna do more hash functions here, G's. These G's are, I think in this analysis, truly random. And what do they map to? I think the G's map to, I guess, the universe of keys. And then they are just hashed to a sufficiently large domain. I think in the paper they just call it integers bounded by R. Say, maybe think of R as something sufficiently big. Just have something in mind. Okay, so with this extra G, what are we doing? So what we're doing is that we're saying here. What we're doing on, say, for instance, an insert of a key X and a value B, we loop over the rows, and then we get the cell. I click 4. And then we do the same with the key sum, the count, and the value sum. Let me just hope you remember. And then we do the special things. We do the hash sum. Of X. Special thing. The deletion is the same. So maybe let us just have a look at how could you now do the get operation with this. We're going to use this hash field to protect ourselves in some sense from these false deletions. So how could we do a get? Any suggestions how to change it, right? So before we're probably still gonna loop over the rows. We're probably still gonna get this field. Like this. What do we do now? Now checks. I think would make sense. So we had it. Okay, let me just start by writing some of the things we did last time. We checked if the count was 1. And we wanted to do something, right? And before, what did we do before?
Yeah. It's almost equal to
Yes, we can still check that. So then, if this is the case, is it safe to just return the value sum now? Key sum is to x. The count is 1. Could this happen for other reasons than x actually being there?
Yeah, it could if you have two keys and one key in there and you delete one there isn't there. And go on.
Yes, yeah, something like this, right? So maybe we could have, I think because the count has to end up at 1, so maybe we need to have 2 keys there. I think something like this, maybe like we have maybe an x1 and an x2, and it just so happens that x1 plus x2 is equal to x, and then maybe we have a false deletion of some x3 that also hashes to this position. Then x1 plus x2 minus x3 is equal to x. If this is the case, then because we add this to the key sum, we add this to the key sum, we delete this from the key sum, and this could actually, by accident, look like x. Could be the case. So we need to do a little bit more, and what we do is check that the hash sum. Yes, we could. There are several ways. We can maybe just check it on what's stored there. G of. Makes sense. We're kind of doing a sanity check that the hash sum that we store here. No, this is wrong. Just the hash sum. That the hash sum is equal to G applied to the key sum. Like this. Then I think we're safe to return. So maybe it would make sense to make this check before this one. Anyways, does it make sense? We can have a look here. We want to check, is this kind of a consistent cell? Like compare the hash sum to G applied to the key sum. I think actually I want to do it before this one. Because I also want to say if the count is 1 and it's not, I also want to be able to return. So we check here, and then we can do the comparison on there. So this is checking, is this a valid cell? Then we can say if key sum x, return the value sum. And else is, you can also return not there, but we found someone else. Makes sense? So we're kind of checking for consistency. And is if the count is 0, I guess we could also check here and let's just say the hash sum is 0. Then we can also say not there. Finally, I guess if we get all the way out, we say no. Something like this. Does that make sense? We basically have the same checks as before, except we just do a sanity check that this looks like it's supposed to, that the hash sum actually equals G applied to the key sum. The intuition, I guess, being that this will almost always be correct. It will only be equal in case we don't have any false kind of deletions that are messing it up. So, of course, we can try and analyze this. So, okay, so maybe so I guess we can say if you have a row where my key does not collide with anyone else, where anyone else is both those that have been inserted, but also those that have been falsely deleted. Right? If I don't collide with any of the two, one of the rows, then if I was there, my count is going to be 1. The hash sum is going to be to G of the key sum, and I'm going to be correct. Make sense? But if I have a row where my key X does not collide with any falsely deleted or any actually inserted items, then I will return the correct thing in that row. Does that make sense? So now we just want to argue it's unlikely that something like this happens that makes us return by accident, because all the rest of the analysis we can still do, right? We already did the same analysis before. We just do a union bound for every row, show what's the probability I collide with someone I'm not supposed to collide with, because now the total number of false and the actual elements is still at most the threshold, so that's all fine. So the only thing we have to worry about is that we accidentally pass this check when we're not supposed to pass this check. Make sense? Chance that we accidentally pass this check. Right. I think I just want to sketch how we can analyze it. So basically we can say, okay, so how could this happen? So basically let's say, so the G functions not depend on the H function, the hash functions H. You can say, like, no matter what the outcome of the H hash functions are, we want to show it's very unlikely this check passes in an example like this. Maybe we can think of it as the hash functions h1 to hk are fixed, and now we're looking at the randomness over the G function. What is the chance that I will pass this check for a given key X in a given row? Basically, all we have to say is, okay, what is the chance that there are keys that have been inserted and deleted? They sum to X, but they're not X, right? And then, but then the G of this key sum should still equal X. So what is the, so let's say we have some keys. J, where this has, some of them have been inserted, some of them have been deleted. We know that the sum of these, we can say sigma is whether it's been inserted or deleted, so it's either +1 or -1. They have this property. And now what we're looking at is, so the hash sum in this field now, the hash sum that will be stored is the sum sigma I G of xi. And this is what will happen to the cell when we're building it, right? So all the insertions will add the hash value of xi to the hash sum. So this is c.hash sum. And we want to compare this E of x. We're looking at what is the probability that these two things are the same. Make sense? So let's say x has not been inserted. Like let's say x is not among x1 to xi. I can even say, like, okay, so there has to be one of those xi's that is not equal to x. Okay, so there is an xi that's not equal to x. Must be at least one of them that's not equal to x. Otherwise, everything is fine, right? We're just at one key that is hashed here and everything's okay. But at least one of them is different. And let's say this key function is truly random. Right? So what can we say? So we can think of it as, I guess you remember from maybe the first lecture we looked at, G, we can kind of look at what hash values does it give on the entire universe U. All these hash values are independent, right? And then let's say this entry corresponds to xi, x, and all the others. One way to think of it is, let's assume that all the other, let's say we condition on the hash values of all the others. So let's say all of these have already been chosen. Everyone but xi have already been chosen at random. Xi is still independent of all the others and uniform random in the output domain. Does that make sense? If I tell you all the other hash values, the hash value of xi is still uniform random and independent of all the others. Also, g of x has been fixed to some value. So what I can say, what is the probability now that over the random choice of xi, or the g of xi, that the hash values, these two will be the same? There's only at most one possible value of the hash function that will make it the same. There's only one value that makes this sum equal to that sum. And I'm choosing my output value uniform random amongst r choices. So the chance that I get that one value is at most 1 over r. That makes sense? That this random hash value makes them look identical. And so there's most of 1 over r chance that g of xi is such that this whole sum is equal to that sum. This is because we have this truly random hash function, and we can just think of the hash values as being drawn one at a time. And after everything but g of xi has been drawn, g of xi is still uniform random. And there's at most one out of r values that makes them this check pass. And now you can union bound over all the steps of the algorithm and all the times you do your get operation. And if you set r sufficiently large, you'll never get this mistake. You'll never will probably say number of operations divided by r is the probability that it will ever happen that you accidentally pass one of these checks when you're not supposed to. You can do the same with this down here. The count is 0, but there were actually falsely deleted elements. There has to be some number of elements. Half of them has been inserted, half of them have been deleted. The hash sum is the sum of these g's. And you can again say, well, you can kind of think of it as all these hash values are being drawn. And then you get to the last one. And there's at most one value that makes the entire sum be the same, like minus the same and as this also happens. So this is basically a way to fix it by just adding these hash sums and checking against this hash sum. The last thing, I guess, then you can think about how can you modify the list entries operation to also work. You do the same with these hash sums, and then you can do something special. Whenever you see a count of -1, then you can think, oh, this was a falsely deleted element. Let me insert it to cancel it out. Does that make sense? So you just kind of do the same algorithm, but you also look for counts of -1s. When you see a -1, you can, and the hash sum checks out, you can then insert it again to kind of simulate removing the false deletion. Basically the same in business. So those are the ideas in this Invertible lookup tables. Anything that's unclear now? Anything you want to ask before we stop? Yeah.
Values or input?
Yeah, the hash values. Yeah.
Should it be R than W?
Okay, I think the U refers to the size of the universe, and then each number here is a number in R. Every number in an entry. So I think I'm just saying, yeah, okay, so maybe
so it's the values of X, not the value of the hash function.
I think what is stored in this entry is G of X. Is the first of X. So that's how I visualize. So there's an entry in this one for every element of the universe, storing what is the hash value assigned by G. So the length of it is the size of the universe, and every element is a number from 0 to R. Maybe one last comment. Oh, stop. If you have these key sums and these value sums, right, where you add up numbers. If this overflows, maybe this can cause issue in your programming language. You could maybe just an interesting hack is to use an XOR instead. Do a bitwise XOR instead of doing addition. So then, I forgot what is XOR and head equals. Just head equals X if head equals B in your C. XOR, with B and you XOR with X, then the deletion is the same actually. So if I XOR twice with the same number, you don't need overflows. So you don't actually need to use a bigger bit number representation. You can do the same with the hash. So just a small practical hack if you watch it. Any other questions? So see you again in a little while. There's a break and Jan is lecturing next week. So.